Hi, this is Mrs. Basin, and in the screencast we're going to talk about the ideal gas law. So we've already talked about the combined gas law when you have two different sets of conditions. The ideal gas law is a little bit different because it's only used there's only one set of conditions. Now before we look at the actual ideal gas law, let's talk about what an ideal gas is. So an ideal gas is a hypothetical substance. So you'll hear us later on talk about real gases versus ideal gases. But for now, we're going to assume that all gases behave as ideal gases. So it is a hypothetical substance. We have real gases, but we don't have these ideal gases. But again, making the assumption that real gases are behaving in this way. So basically, they are particles with zero volume and no attraction for one another, which is something we've kind of already talked about. Ideal gases conform to what's called the kinetic molecular theory. So these are the 5 points of the kinetic molecular theory. So the first one is gases consist of tiny particles. The measurable volume of a gas is zero. The gas particles are in constant motion. The particles don't attract or repel each other, and the average kinetic energy of them is directly proportional to the temperature. So these are going to sound a lot like those properties that you wrote down one of those first days that we talked about gases. So some things that could also affect their kinetic energy is that they have a greater mass or velocity. So the larger gas molecules or the ones that are moving faster, they're going to have a greater kinetic energy. So a higher temperature gives them a higher speed, which is going to give them a higher kinetic energy. So here's the ideal gas law. So this is a gas law that describes the behavior of an ideal gas. Now this law is a little bit different because things do have to be in certain units for the calculations to work out. And that reason is we are using what's called the ideal gas constant in the ideal gas law, and if you notice in that ideal gas constant, there are units, kind of a weird unit associated with it. So the ideal gas constant is something that's used when you calculate an ideal gas, properties of an ideal gas, and that's 0.0821 liter atmospheres per mole Kelvin. So that big mess of units at the end is actually the unit for the ideal gas constant. So because of that, the other things that you put into that equation have to be in certain units. So the pressure has to be in ATMs, volume has to be in liters, N has to be in moles, and temperature, as always, has to be in Kelvin. So the formula for this then is PV equals nRT. And you can see above there what those different variables stand for. The P and the V and the T and the N we've already talked about. And then, like I said, the R is that ideal gas constant. So let's do a couple example problems. So we're going to start these the same way that we started the other ones, where we're going to make a list of our variables. So for this one, we want to know what volume, let me switch colors here, what volume, so V equals, question mark, is occupied by 0.25 moles, so N equals 0.250, of carbon dioxide gas at 25 degrees Celsius, so temperature 25 degrees Celsius, and pressure 371 torr. To moles. Okay, so like we said, we have to check our units here. Volume, once we solve for it, will come out in liters, so we're okay there. N is already in moles. Temperature is in Celsius, and we know to get to Kelvin, we have to add 273. So that comes out to 298 K. So that's our temperature in Kelvin. And then pressure is in torr, and like we just saw, pressure has to be in ATMs. So we're going to do a conversion here. So 1 ATM is equal to 760 torr. So we end up with 0.49 ATMs. Okay, then from there, all we have to do is put those into our equation. So PV equals nRT. Our R value is a constant, so we'll put that up here. R is always 0.0821 liter atmosphere per mole Kelvin. And we'll see how that fits into our equation here in a second. Okay, so our pressure we're going to put in is 0.49 ATM. Volume is what we're solving for. Moles, 0.250, and I'm going to run out of room here to put units, so I'm going to stop doing that. 0.0821 for the R value, and then the temperature is 298. So then from there, I'm going to go through and solve for volume. If I could get all those units in there, everything would cancel out except for, except for liters, because this is liters ATM per mole K. So I would be left with liters. So my volume for this one ends up being 12.5. Okay, so let's go on and try another one if you need to. If not, you can skip ahead to the next section. Okay, so here's another one. This one talks about radon, which is a gas formed in the soil. This is something that can seep into basements, and a lot of times you can have your radon levels in your house tested. If you move, a lot of times that's a requirement where you have to have a sensor put in your basement to check for radon, and it can be dangerous because it can cause lung cancer. So if we have this particular gas, we have 1.5 moles of it. So we're going to start our list again here. So N equals 1.5 moles. And it has a volume of 21 liters at a temperature of 33 degrees Celsius. And we want to know what is the pressure of this gas. Just like always, we're going to use the same R value, 0.0821 liter ATMs per mole K. Okay, the only one we have to fix here, we're already in moles for N, liters for volume. We have to add our 273 for our temperature, and that comes out to be 306 K. And then our pressure is what we're solving for. So same formula again, PV equals nRT. Pressure is what we're looking for. Volume is 21, N 1.5, R 0.0821, T 306. Again, when we go through and solve, our pressure ends up being 1.79 ATMs. Because once we cancel all those units out of our ideal gas constant, ATMs is what's left.